Good day, everybody. We are expecting some more people to join actually. So I'm sorry, we'll be waiting for another 2, 3, 5 minutes. Zbigniew, do you hear me well?
Yes, I hear you loud and clear.
All right, great.
Hi, Valerie. Good afternoon.
Hi. Hello, everybody. Um, I don't know if well, I can make some introductory words before the others come. I don't know if you have participated in our webinars previously. We decided to record this one at least. We also recorded some others. And today we are also trying to stream it to social networks. Um, well, typically it's a friendly atmosphere. If you have a question, please feel free to, asking it at the right point during the presentation. So there are no particular rules. And I believe it is going to be interesting because I know that Zbignev's solution is quite unique, actually, as well as our technology. So today we have a special guest, and I'm very happy to introduce you our CTO of our partner company, Zbigniew Lapkiewicz, the CTO of NetQPro, who will be the main speaker during this webinar and present the merge of NetQPro call quality monitoring and analysis system with our technology for measuring quality of user experience or caller experience. Zbigniew, you're very welcome, and the floor is yours.
Thank you very much. Thank you. And good afternoon to all of you. Let me share my screen with my presentation. I hope you can see it now. Okay. Hope you can see my screen. And yeah, let's start. So during this presentation, so first of all, thank you very much for inviting me for this webinar, and thank you much for the opportunity to give you some kind of testimony about how we actually use PVQA in our system, and also give you some few words about our system itself and our experience with PVQA. So I really hope it will be interesting for you. If you would have any questions, feel free, of course, to ask me. I will be more than happy to give you some more information. I will start with a very short introduction of our company, just to tell you who we are. Then I will tell you how our story with Savannah, as they began, so how we actually started our cooperation quite many years ago, because I think it was 7 or 8 years already. Then I will tell you how the PVQA is embedded in Nscan, so actually how it is implemented and how it is actually interwork with the rest of the system. And at the end, I will also tell you a few words about Nscan itself, just a few slides, just to give you some more impression, what's our system, what we can do. And I hope at the end we'll have plenty of questions. Then, of course, I will be ready to answer, and then stage will be basically yours. So who we are. NetQPro is a company which was founded by a group of engineers from Poland almost 10 years ago. So next year will be our 10-year anniversary since actually we started our operations. And we are fully focused on development of what we call Nscan network monitoring system. So this is basically the passive monitoring system dedicated to monitor telecom networks, mobile and fixed networks, which is already implemented in, let's say, number of operators. The first system was actually successfully deployed just 1 year after the company was established, and that was a countrywide deployment at shared radio access network of T-Mobile and Orange in Poland. So pretty huge network, more than 30 million subscribers. That was really a big success for us to make the system ready in such a, let's say, short time. And today, our systems are already used by a number of operators in Europe, Middle East, in East Africa. We have also one operator who is actually covering pretty big part of the earth from Europe east to Australia as satellite operator. So I could say that even Australia and Asia is covered, but it's of course not really true. So if you're interested in more information, please visit us at www.netqpro.com, where you can find more information, and you can also contact us, let's say, directly. Later on, I will tell you a few more words and show you some few slides about the system with some details. But just to give you some impression, what is Nscan? It is basically a real-time network monitoring system for the quality assurance. This is how I would call it, just to name it, let's say, in one sentence. The system today supports both CS and the PS core network interfaces, all of them or most of them. So we are supporting, of course, ISAP, SIP, MAP, CAP for the CS service, GTP, GTP1, GTP2, diameter, SV, and all the other interfaces. For the PS network, we are also supporting, of course, NGN protocols like Megaco, like SIP. So there's actually much more than this. What's pretty what's actually very important from the users of our system is that we are providing also the full end-to-end correlation of all the messages, which are also, let's say, decoded down to the bit level. So actually the user can see the given service for the given subscriber really end-to-end on all the interfaces, starting from the radio access network up to, let's say, the core interfaces, all of them, let's say, correlated. And one that's pretty unique is the feature which allow you to make a on-demand online tracing of the given subscriber. So basically the system user can just specify the subscriber, can enter IMSI or MSISDN, and then in real time, all the activity of the subscriber will be actually visualized. You will see all the messages fully also correlated and also fully, let's say, decoded. Nscan process not only the control plane, but also the user plane, which of course is a big challenge, assuming that the volume of the content of this communication is much, much higher than the signaling, especially in case of PS data. We are talking about hundreds of gigabit per second per site, and let's say per network. We have customers where this total volume of traffic is close to 1 terabit per second. So it's really huge volume. But also for the CS, this content monitoring is important. Actually, this is where we are using PVQA from Savannah. And this is what I will tell you actually more. Nscan actually started from monitoring of radio access network. This is actually our first customer. The main or the key requirements of our first customer was actually monitoring of RAN, especially as it was a shared radio access network. So the RAN, which was used by more than one mobile network operator. So this is what we support. Nscan, on top of, let's say, the sessions which are recorded, which can be visualized, also provides number of KPIs, which can be used for the real-time alarming. And we are also providing XDR streaming, so those can be actually exported to some third-party systems as well. And this is an open architecture, which is ready to deploy some new features. And coming to our main subject, necessity is the mother of innovation. This is the truth which everybody knows. And this exactly explains how our journey with Savannah began a couple years ago. One of our first customer has a very special problem, very specific problem, and that was a problem with silent calls. You probably all know that bastard. The silent call is this kind of a call, this kind of a service, where from the control plane it looks absolutely perfect. So we have a call which was successfully established. All is nice, except that our subscribers do not hear each other, or maybe only one subscriber hear the other one, or maybe there is some just noise instead of this bidirectional communication. As our system was monitoring just the control plane, so all looked perfect, and we were totally blind for that silent call. So our customer was, of course, not happy because they knew that there is a problem, and from the system, we couldn't actually see this. So we realized that control plane monitoring is just not enough. And if you really care about the quality, and of course, the only way is to actually move a step further and also to analyze the content. So this communication, which is exchanged between our subscribers. So we implemented RTP analysis, but RTP, that was a mobile network, RTP comes from the BSC or RNC, while our, let's say, silence problem was somewhere deeper in the run. So even just RTP analysis, which normally solves the problem in case of like a VoIP networks, this RTP analysis was not sufficient in case of mobile network, so we were still blind. And then we understood that only audio analysis will really solve the problem. We start searching, looking around, and this is actually how we found the Savannah, who actually offered PVQA and analyzed not just the transport network, but analyzed this, let's say, embedded audio. So let's talk a bit more about voice quality assurance, and let's talk about the problems which are behind this voice quality assurance. First, what we are monitoring the network, and this telecom network is really complex. Network is a chain of elements which is often delivered by various vendors, which is from like a different, let's say, technologies from different, delivered at different time. So the problem is very often with the compatibility of those elements, and a lot of problem you can find somewhere on the edge between, let's say, two systems, especially if you have some legacy systems in your network. Nowadays, those network elements are not simply connected like it was in the past, let's say, with dedicated wires, dedicated like a PCM links like it was in the past. But in fact, we have a number of network elements which are connected over, we can say, IP cloud. So basically, there is like a backbone communication network, which can also be responsible for a number of problems, especially in case of bigger traffic. In modern network architecture, control plane and the user plane, so signaling and, for example, voice, is processed separately. Like in a CS, like for the CS services, we have a media gateway which processes the voice, and we have a MSS, which actually processes the signaling. So this is another source of potential problems, which can lead to the problem like a silent call, for example. And last but not least, we do not use the single codec to encode our voice, but there are a number of codecs which are used today in the mobile networks. Just in a GSM network, or basically in a 2G, 3G network, we have at least four or five actually different codecs, where 3G brings another at least 2 codecs. And now in the era of Volta, where actually we also have this somehow combined with IMS services, we have another, we can say, tens of codecs which potentially can be used in this chain of our telecom networks. So another problem comes from the fact that those codecs that we need to, that sometimes we might have interworking between, let's say, different codecs, and transcoding is required. Also, those codecs may dynamically change the encoding mode, which also gives, let's say, which also can be a source of the problem. And of course, much, much more. So if we focus just on the speech quality, and if we even forget about that the given call for some reason might not be, let's say, set up properly, you can see that there are at every point of this network, we might have some source of the problem. At the source, so at the UE directly, at the terminal, we can have some quantization errors, which are just natural for every codec, so it depends on the codec. This quantization error can be different. We can have some echo issues. We have some delay, which is caused by the codec itself. And then in the rest of the network, we can have a problem with dropped packets. We can have a problem with jitter, or let's say delay. We can have a problem with transcoding over those codecs. We can also have a problem coming from the transport network, like a drop packets or some routing delay. So there are a lot of issues which might impact our voice, and which might cause that either this voice will not reach destination, so we will have this classical, let's say, silent call, or the voice will arrive so corrupted that our subscribers will be definitely not happy from the quality of the service. So how to actually measure the quality? Typically, what we use from many, many years is an index which is called MOS. MOS, which stands for Mean Opinion Score. This is the measure of the subjective quality of a human speech, represented as a rating index. Important here is subjective, because MOS, Mean Opinion Score, supposed to be kind of the estimation of the quality given by human listeners. So the only true MOS result can be given by the human. Someone hears the given communication, and he can say, okay, that was perfect, I give 5, or it was bad, I give only maybe 2. Yeah? This is subjective. The same conversation for some people might be absolutely perfect, some others might don't like it. Yeah, so it's subjective. It is not like that the given call will be let's say qualified or quantified by number of users in the same way. So this is somehow the first problem. MOS is represented as a kind of index in a range from 1 to 5, like in a school. 1 is the worst, 5 is the best. And typically, or in the past, the toll quality was set for 4. So if the quality was better than 4, then our listeners, our subscribers should be satisfied with the quality. If it's below 4, they might hear some they might not fully like, let's say, this quality. Well, nowadays we are not really focused on this 4. Typically, in the mobile networks, we accept even lower quality. It also depends actually where our subscribers are using the service. They have a different expectations if they are sitting in a quiet, let's say, home, and they have a different expectations when they are outside, where they are, for example, driving with the car or with the train. Then, of course, the expectations are different. There are, of course, several algorithms which can be used to estimate this mean opinion score. Estimate, so it is always estimation, not the absolute, let's say, value for the mean opinion score. But almost all the standardized algorithms are based on what we call a reference model. So the model which is comparing what was sent, what was received, with what was sent. So reference assumes that we have a reference. We know what kind of voice sample was somehow inserted to our network, and we can compare what comes out of the network. We can compare with the source and estimate how it was degraded. So from our perspective, as the vendor for the passive monitoring system, is that the reference model cannot be used in case of passive monitoring because we don't know that voice. We don't know, let's say, what sounds, what voice was inserted to the system. We can only monitor passively what is transported over our network. So all of the standard algorithms can be used in active testing, where we have some active testers who send the voice and monitor what was received. But in a passive monitoring, this, of course, cannot be used. But even if we would have the MOS, if we would know somehow, let's say, the MOS, then this MOS is not enough. MOS gives just estimation of the quality of experience. It tells if our subscribers are somehow satisfied from the quality of the network or not. But we don't know what was eventually the root cause of eventual problem. So it is good as a kind of executive level report, just to as an indicator if everything is good or not, but it is not enough for engineers. Network engineers actually need to do the troubleshooting. So they need to know the details. They need to actually understand if this quality was degraded by, for example, jitter or delay, if it was degraded by, I don't know, lost packets, or maybe there is a noise which impact the quality, or silence, opposite, or maybe there are some impairments like a clipping or clicking, which might indicate some loss of given packets. Having this data information, they can take some action and they can somehow identify what could be the reason for the problem. And also, all of those informations like MOS and the detailed parameters need to be aggregated at the network elements, just to isolate this network element, which is guilty, which is actually responsible for the problem. We need to aggregate for location, just for example, to identify the sites, the cells, where the quality is worse than in the others, or even aggregated per user equipment, like a type of the phones or brands, just to eventually correlate the problems with a particular phone, which might impact the quality in overall network. So PVQA give us the measurement, and the system actually processed all the informations just actually to give this extra information. So let's have a look how PVQA is implemented in our system. Well, in the mobile networks, the best or the most efficient way to monitor both the control plane and user plane for the CS services are the interfaces between RAN and core, because this is where we can also see the impact of the RAN, and we can eventually see the impact of the core network. We can distinguish this, and this is basically that point where we can see all traffic. In the core network, you might have CS calls being processed by the different technologies, but at the end, all of them will actually go through this RAN to core interface to reach our subscriber. So typically, A and IUCS interface is the best one for processing this control plane and user plane together. In case of Volta architecture, we typically monitor the traffic between SBC and the rest of IMS network. SBC is a session border controller. According to IMS technology, this is proxy CSCF, so this is this element at the edge of the radio access network. And again, this is the interface where actually we have correlated also control plane with the user plane, so typically SIP with our RTP with media, and this is also the best interface to process. So in all of these interfaces, both control plane and the user plane need to be processed in a correlated way, of course. We need to decode voice, and this voice needs to be analyzed. And this is actually the key for success, yeah? Because when we get this voice, regardless how it is transported, we can analyze this and gives the true information about quality. Well, let's have a look how this voice is really transported in our network. Let's take an example, IUCS interface, which is actually a bit more complicated than the others. In a VoIP network, it's slightly more simple, but the general rule is more or less the same. So this is what you see. It's a kind of the protocol stack, which illustrates this communication. On the lowest level, we have IP network, which is just route our packets from the source to destination. For example, from RNC to maybe media gateway. On top, we have a UDP protocol, which is used to identify every single RTP stream. So between this RNC and media gateway, we can have hundreds or even thousands of those, let's say, tunnels with voice communication. And the UDP port is actually used to identify or to distinguish one from another. And we have RTP. RTP, which stands for Real-Time Transport Protocol. It is a special protocol which gives some extra information about what is transported on top. We have, first of all, a real-time marker, so we know when this packet was sent. Based on this timestamp marker, we can calculate delay. We can also calculate jitter, so it's very important for calculating the quality. We have also kind of the sequence number, so we can actually calculate, we can actually find out that some packets were lost. And then on top, we have embedded media. Depends on interfaces, it looks different. On IUCS, we have a protocol called IUUP, which is also used to carry some additional information of what mode of the codec is being used. And finally, we have a codec. So we have our speech or voice encoded with the specific mode. On IUCS, so in 3G, we typically use the codec which is called AMR, or Adaptive Multi-Rate Codec. Adaptive, which means that this codec can encode the voice with different modes or with different speeds. To make it more simple, depends on many factors like quality, but also depends if we actually transport, for example, silence information, like a comfort noise, or if we transport the real, like a speech. So this encoding may vary from few kilobits per second up to 40, if I remember, 42 kilobits per second. So this range is pretty high. And this needs to be, of course, processed. So first, our system needs to analyze IP and RTP just to track every single call separately. Then we need to process IUUP to get the information what codec and in which mode is being used. And finally, we need to get our encoded data decode this data and get what's supposed to be our audio. Let's put it together. And this is how actually PVQA is embedded in our system. So we are processing both control plane and the user plane. From the control plane, we are getting the information actually how our voice is being transported. So we can get the information about codecs being used and the transport information, how it is transported. So having this information, we can decode our voice, which means we can track every single RTP stream with our voice, and knowing the information of what codec is being used, we can decode this voice. So at this stage, we have something like an audio. It is still, of course, encoded, but it is an audio. And now we are processing, or actually this is where PVQA jumps on the stage. PVQA do the waveform analysis of that audio, and it's actually looking for some kind of impairments with this special algorithms which are embedded in the PVQA, which were developed by Savannah engineers. They are detecting a number of different impairments, like loudness, like signal to noise ratio, like clipping, like echo. And based on all of these impairments, they estimate this MOS. So at the end of the day, for every analyzed sample, we have this high level MOS value. But we also know those details, like we know if this degraded quality was caused by silence, or maybe was caused by clipping, or maybe by some other sort of the problem. Physically, it is implemented in a way that our Nscan monitoring system normally processes the control plane. So from this control plane, we are actually getting information that the call was started. And of course, depends on where we are monitoring. We process either BSS map, if it's 2G, or run-up, if it's 3G, or SIP, if it is, for example, VoLTE or simply VoIP network. From this information, we get information about our transport addresses and about the codecs being used, and we can start tracking those uplink and, let's say, downlink streams. And what we are doing here, we are implementing the sampling. PVQA can actually process the complete call, but we have decided to implement here a sampling. Why? I'll explain it later. But basically, at the given time, we are taking the sample of this conversation. The sample can be between 15 seconds, typically up to 30 seconds. And we are decoding this sample and doing its analysis. So having the results, we can use those results to build the KPIs, which are calculated and aggregated per cell, so per location, per network element, like per media gateway, or per given like user terminals. But we also put that results associated with, let's say, every single call. So together with our call transactions is simply expanded also with PVQA informations. Why we do the sampling? Due to performance reasons, simply. From statistically, if we analyze the sample of the given conversation, we can also get the information which is somehow valid for the complete call. If we get this sample at the end of the call, then we know that even if our subscribers had a bad quality and they decided to terminate this call, we catch this. So typically, we always take a sample at least at the end of the call, but we can also specify some kind of sampling policy to process also some additional samples during the call. So it's just, we can simply configure this. System administrator can configure how he wants to catch these samples. So collected samples, which are at least 10 seconds, are processed by PVQA, delivered by Savannah, and they detect some key voice impairments, like ambient clipping, like a voice activity detection cause clipping, like dead air, which is actually very important from our perspective for silent call detection. SNR, echo, some other impairments are also detected. Those impairments are analyzed multiple times for our sample. So actually this samplification is at the level of, if I remember, 1 second. And kind of average quality is calculated for the whole sample, which was sent to the PVQA server. Of course, the PVQA server is embedded in our system, so it is sent automatically to that server. Of course, system user don't care how it is implemented, so for him, it is important how he can see those results. So he can see this as a kind of statistic. So he can select that, for example, he wants to see average MOS over time. So he can see this as a kind of a timeline. And when selecting the given point in time, we can see also distribution of the quality for source and destination. Also, he can see this quality directly associated with every single call. So when opening, for example, the call table, and when analyzing the quality, basically analyzing the quality, he can see what was the estimated quality for every single call. He can see it, as you can see, for number of sessions. He can also use this for actively for searching the given calls, which are, for example, below the given MOS level. But also when analyzing the call details, he can see, let's say, the signaling call flow, like on this example, some SIP, let's say, messages correlated and visualized together with the RTP stream, where already this RTP stream you can see indicated mean opinion score. So from the user perspective, who is using the Nscan monitoring system, all this high, let's say, technology is really hidden, and the user see just the outcome, so see just the results. Of course, the user also do not need to constantly monitor those figures. There is also alarming mechanism. So as we are calculating KPI per network elements, per cells, etc., the user can also trigger an alarm for an average quality. And if this quality drops below the given threshold level, some alarm will be automatically delivered to the system user. At the end, let me just show you a few slides about the Nscan smart network monitoring system, as we call it, just to give you some impression about the Nscan. So Nscan is, of course, not just a system which monitors quality of CS, but basically it's a system which monitors telecom networks. So our system was developed as a highly distributed and highly scalable. So in our deployments, we have small systems where the whole system is deployed on just, let's say, 2 servers, up to the systems where it is running on more than 150 servers. Depends, of course, on the size of the network and the volume which need to be processed. The idea is that we have local probes which process the traffic, let's say, locally. Those local probes also locally maintain the local database and the storage for the RAF data. So it's all stored locally. On top of this, we have a central server, and the central server is hosting the web user application. So actually users are using the system through the web application, and this central server is actually sending the queries to the local probes to get the results, and actually visualize sessions, visualize some KPIs, well, whatever is requested by our users. Nscan is fully modular. So from the user perspective, there are a number of modules which can be granted for each single user. So actually we can decide, an operator can decide which modules can be used by the given, let's say, user of the system. So we have, for example, session analyzer to analyze the session details. We have a performance analyzer just to analyze the KPIs. We have a traffic analyzer to analyze the user plane, so analyze especially the PS user data. And of course, not every system user need to have access for all of those modules. From the user perspective, there's one single web-based application. When logging to the system, user will see this kind of, let's say, welcome page or landing page, which is in fact a dashboard. All the dashboard, I mean, this dashboard is fully, can be fully customized by every system user. So it's dedicated for every user. User can actually add his own KPIs and put them on a screen. He can resize those diagrams. He can actually relocate them. So it's fully custom made, customized by every single user. Then we have advanced troubleshooting session analyzer. This is basically the module where user can browse and deeply analyze, let's say, in details, all the sessions. There are, of course, a number of criteria which can be used for browsing for the sessions. The most important, like subscriber identities, like IMSI, calling cold party number, duration, time, are upfront. So we do not need to get into details. If we want to search for some, based on some more advanced criteria, there are dedicated windows where all like a core ISAP or MAP or CAP related parameters can be configured. There is also some advanced filtering module where the users can build advanced searching criteria using AND, or let's say other logical operators. And then when we actually define all these criteria, we can press search just to find the sessions we are looking for. Then we can, of course, select the columns. So some most important information about the course will be already visible here. System allows you also for on-demand correlation. So based on embedded criteria, system will actually correlate information, or actually records sessions from number of interfaces which are correlated together. So you can see the same call, for example, on the run interfaces, then on the core interfaces, all linked together. And when you click on the details, you can actually see this single, let's say, call either as a ladder diagram, like on the screen, either in a tabular form, but basically in every form, you can see messages and also message details. So every message is, of course, fully decoded. The next module is a performance analyzer module, where basically we can visualize KPIs. There are hundreds of KPIs which are calculated for all major protocols supported by Nscan. All of those KPIs are aggregated per cell, per network element, per country, per MNO, per many other, let's say, parameters. So we can see those KPIs in a different angles, in a different, let's say, views. And of course, all of those KPIs can also be exported on demand, or can be even streamed if it's necessary for some third-party systems. We also have a pretty advanced run analyzer module. So the module to analyze details of the radio access network. And there's, of course, geolocalized visualization here, but basically you can see the KPIs directly aggregated to sectors, to sites, to some bigger regions. There's also like a detailed view where radio access parameters, like radio parameters, can be also analyzed in a distance from the cell, or you can see some correlation between different parameters. The next module is a module which is based on embedded DPI. As I told you earlier, this is also very important for many mobile operators to analyze the structure of the PS data, not just quality in sense of, let's say, throughput or bit rates, because just the bit rate tells you nothing. If you correlate this bit rate with a given application, like with YouTube or with Skype or whatever, then you can really compare apples with apples. If you compare, for example, YouTube bitrate for one subscriber with a YouTube bitrate with another subscriber, you can see, you can actually find out that some of the subscribers might have a problem. So this is the reason why this protocol classification is important. We are embedding in our system DPI from Cosmos. Actually, we are Cosmos is the name of the product. It is delivered by INEA, a French company, where more than 4,000 protocols and applications are automatically decoded. So using this DPI, a system user can actually analyze the structure of the protocol exchange, for example, between any given network elements. So we can actually see the structure of protocols and applications used by our subscribers. We can also analyze the volume of this data per time. So this kind of timeline. And then when clicking on a specific point in time, we can see distribution per protocols, per IP addresses, per GSNs, per APNs, per some number of other, let's say, parameters. And it's also possible to analyze this user plane per single subscriber. Of course, not every system user might have access for this because it's pretty sensitive data, but those who have this privilege, they can just enter subscriber identity and get the information about volume of data, protocols used, and also the quality. Like, for example, what was the throughput, what was the bit rate for the given cell, maximum and average, which also gives some extra information about quality of experience of the given subscriber. So thank you very much for your attention. Thank you very much for your time, and I hope you have questions, because now it's our Q&A time.
Yes, Zbigniew, thank you very much for the presentation, and I would like to encourage all the participants to ask questions. We all are very eager to answer them. Seems there are no questions. Then, well, I can tell you that if you're interested to learn more, you can get in touch with Zbigniew through their website, or you can always message me and then send an introductory email.
Yes, please. If you have any additional questions related to our system, please kindly contact me directly. I'll be more than happy to give you more information, or we can also arrange a dedicated presentation if you like. So you're very welcome.
All right. Thank you very much. Bye-bye.
Thank you.
Thank you.
Thank you. Bye-bye.
Okay, thank you all for your participation, time, and interest. Maybe see you next time. Zbigniew, again, thank you very much.
Thank you for invitation, and talk to you next time.
Yeah, talk to you next time. Thanks.
Bye-bye.
Bye-bye.